Welcome back. So finally, at the last part of this example that we started 3 videos ago for Green's theorem. This time around, we want to evaluate the integral along the curve x equal to 2t squared plus t plus 1, y equal to t squared plus 1, corresponding to t equals 0 and t is equal to 1, respectively. So this is what we want to use as our integration parameters. Essentially, what this is telling you is for you to rewrite x and y in terms of t, which would also mean we write the bounds in terms of t. Once you're able to do that, then you are good to go. Now, how exactly would you know which of the bounds to work with? The very first thing is you want to work with the bounds that are commonplace between x and y, because you have two variables and you want to shrink them into one. You want to work with common points of intersection between x and y, which is what values of t can you find in the x function and can you also find in the y function. Those values would be the values that would stand up as your bound. So let's quickly check. As always, make sure to like, share, and subscribe, and turn on your notifications so you do not miss any of our videos. Now let's begin. In this case, the very first thing we want to do is we want to evaluate what the values would be at the original bound, right? So you have x equals 2t squared plus t plus 1. Now, evaluating this as x tends to 1, if we put that into this, you would have that you're saying that 2t squared plus t plus 1 equals 1. So that, of course, this gives you a quadratic equation, 2t plus t equals 0, which immediately factorization you have is to mean that t equals 0 or t equals minus 1 over 2. Right? These are two possible values for t in this case. Now, on the other hand, the upper bound where you have x tends to 4, in this case, you're going to have 2t squared plus t plus 1 equals 4. So bringing them all together, you have 2t squared plus t minus 3 equals 0. Now, this, of course, still remains factorizable. And by factorizing this, we have that t would be equal to minus 3 over 2. And then we see that t would also be equal to 1. As always, you can take a pause to break this quadratic equation down by factorization method and see if you actually get the same thing. I'll look forward to your results in the comment. Now, let's continue this. We have this for the y perspective, for the x perspective, sorry. On the y side, we have y equal to t squared plus 1. Now, in this case, where we said y to be equal to 1, we have that t squared plus 1 equals 1, which would mean immediately that t squared will be equal to 0, which would mean that t will be equal to 0 twice, right? So it will be a double solution for 0. Similarly, when y goes to its upper bound, which is 2 in this case, we will have immediately that t squared plus 1 equals 2, which would mean that t squared minus 1 equals 2. This is the difference of two squares. So the roots would be t equals minus 1 and then t equals 1. So this is what we have. So we would now specify or prioritize picking the common points between x and y, which in this case is 0, right? 0 is the common lower point, and then 1 is the common upper point. Of course, there is minus 3 over 2 and minus 1 over 2, but these two are just x values. They don't share any correlation with y. Similarly, t equals to minus 1 in y, they have no correlation with x. But the values that are commonplace in x and y is t equal to 0, which also occurs in y and x, and then t equal to 1, which occurs in x as well as in y. You would also notice that the position of the common terms is coming at the same position in terms of it being a lower term or an upper term, right? So if you had that t equal to 1 at x tending to 1, that would have been a problem because x tending to 1 is a lower bound. So t equal to 1 would have been a lower bound. But then t equal to 1 is occurring at the upper bound of x as well as at the upper bound of y. So it means that t equal to 1 is indeed an upper bound to be kept in mind. So those are very, very important things. So in this case, we have those two. And of course, we can find out what the x would be and what the y would be, right? So since x equals 2t squared plus t plus 1, and you have that y, of course, equals t squared plus 1, we have that dx will just be the differentiation on this side. That would be 4t plus 1t, and then on the y side, we have that the y will be 2t. These are the two values we need. Now that we have that, we can now go ahead with our substitution. So I, which of course we've made equal to 1142 x plus y dx plus y minus x the y. If you're wondering where we started using these values from, check our previous videos where we started the examples of this Green's theorem. So that will definitely prove a lot helpful. Now let's continue. So in this case, this would now reduce into the integral from 0 to 1 based off the t values, integral from 0 to 1, and then wherever we see x, it is replaced with 2t squared plus t plus 1. So that will be 2t squared plus t plus 1. And anywhere we see y to be reduced or replaced with t squared plus 1. And where we see dx, it will be replaced with 4t plus 1 dt. And then on the other side, the same thing will happen, which is this one. We're going to have y minus x, so that's going to have t squared plus 1 minus 2t squared plus t plus 1, and then dt, the y in this case would simply be 2t dt. This is what we're going to have. So we can, of course, go ahead to expand this, right, so that we can see what the final result will be. So if we do, we have 0 to 1. So if we do, we're going to have integral from 0 to 1. On this side, of course, the inside, of course, gives you 3t squared plus t plus 2. And then outside is still 4t plus 1 t. And then on this side, we have integral from 0 to 1 minus t squared minus t, right? Because 1 minus 1 gives you 0. And then t squared minus 2t squared gives you minus t squared. So, and then you still have 2t dt outside. So bringing it all together, expanding this, you'd have 0 to 1, 12t cubed plus 3t squared plus 4t squared plus t plus 8t plus 2t. And then you have plus 0 to 1 minus 2t cubed minus 2t squared. So I in this case, which is of course the original integral, would simply be integral from 0 to 1 of 12t cubed, right? This is plus 7t cubed, t squared. So you have 12t cubed. You could already combine them together if necessary. Minus 2t cubed, right? Plus 7t squared minus 2t squared plus 9t plus 2 dt. So I will be equal to, this is 10t cubed, that's integral from 0 to 1 of 10t cubed plus 5t squared plus 9t plus 2 dt. So now let us see if we can evaluate the final result as the case is. Now, if we have this and we wish to evaluate the final result, what we are going to have is very, very simple. What we are simply going to have in this case is to evaluate this using our basic algebraic method of integration that we always use. Now, let us proceed with this. So I, of course, integral from 0 to 1, 10t cubed plus 5t squared plus 9t plus 2 dt. This would give us 10t raised to the power 4 over 4 plus 5t cubed over 3 plus 9t squared over 2 plus 2t. All of this evaluated from 0 to 1. The lower bound, which is the 0 part, vanishes everything because of the presence of t in all the terms. And then so the upper bound remains as I equals 10 over 4 plus 5 over 3 plus 9 over 2 plus 2. This is what we're going to have as the upper bound. And of course, if we take a direct LCM, you have the LCM of this. You have the LCM of this to be 12 in this case. So you have 30 plus 20, right? Plus 54 and then plus 24 as the case is. So if we add all of this together, we have our term to be 128 divided by 12. So that means that I, or therefore I, would simply be equal to 32 over 3 in, of course, lower terms, right? Which is, of course, dividing by 4 here. So 4 in 120 gives you 32, and that's as low as it can go. So what have we achieved so far in all of our explanations of these examples? We have shown that, first and foremost, the evaluation of the integral can be split into the integrals based off the variables, right, by simply understanding the pathway to which the integral is to be carried out. Then two, we can also evaluate an integral based off several paths, and the results of the evaluations need not be the same across all the paths that we evaluate on. Now, of course, this refers to something different when we want to evaluate across a single path, right? And we want to verify that the integral around that single path exists, right? This will be done much later when we consider the concept of the Cauchy's first integral theorem. But first and foremost, we have taken a very, very in-depth example as regards to the Green's theorem. Now, this is, of course, the example we have discussed. Now, as a practice, before you move to our next video, you can try your hand with this example and see if you would be able to solve it. And then look at our next video for clarity as regards to how this example was done. The next video will be the long form to carry out the solution to that example at a stretch. So here it is. Evaluate the integral 2x minus y plus 4 dx plus 5y plus 3x minus 6 dy around a triangle of vertices 0, 0, 3, 0, and 3, 2, transversed in a counterclockwise direction, and then a circle of radius 4 with center 0, 0. So please try your hand on this. Once you have an answer, continue on with our next video to see how we solve this problem. As always, make sure to like, share, and subscribe, and turn on your notifications so you do not miss any of our videos.